I also want to emphasize the importance of simulation. It's got a twofold purpose. One purpose is to make sure that the theory that you're doing is right. If the simulation matches the theory, that gives you confidence in the theory. Another purpose of simulation is that you can use it even when the theory is too difficult and still get some answers. Sometimes you can still do simulation. So in the problem on the homework, we had a random variable, capital T, representing, in this case, the lifetime of a washing machine. I could have said it was a refrigerator, but I picked a washing machine. It's got a certain PDF that you're given, probability density function, little f of t, that's taken to be a formula t over 200 if t itself is between 0 and 20. And it's technically 0 otherwise. Now, I didn't write it as a piecewise formula on the assignment, but technically speaking, that's what's going on. It's t over 200, excuse me, if t is between 0 and 20, and is 0 otherwise. Graphically, the probability density function looks like this. It's 0 over here when t is negative. It's 0 over here when t is bigger than 20. Technically, you could put an open circle here and a closed circle here. It equals t over 200, a line through the origin with a slope of 1 over 200 if t is between 0 and 20. You didn't have to do this, but it might be worth realizing you should or could check that this is a probability density function, that the total area under it is 1. And you don't even have to do an integral here because the shape is a triangle with base of 20. And what is the height? Plug in t equals 20 into that formula, you get 20 over 200 or 0.1. 1/10. The area of the triangle, 1/2 base times height, is 1/2 times 20 times 0.1 is 10 times 0.1 is 1. That's the area under this graph. Therefore, it can serve as a valid probability density function, meaning it satisfies the laws of probability. It doesn't mean it's a good model for washing machine lifetimes. Probably is not a good model. What is it implying as a density function? It's implying, since it's higher near 20 and lower near 0, that most of the washing machines last close to 20 years, but then none of them last past 20 years. Like they have a self-destruct when we reach t equals 20. Maybe that really happens. I don't know. Very few of them where the density function is lower have a very short lifetime. Okay, so maybe it's accurate if they have a self-destruct at t equals 20. I hope you realized in trying to solve the problem that you had that it's useful to find the CDF for this as well. The CDF, capital F of t, by integrating the PDF. Although it might be useful for purposes of relating it to the present value random variable, to remind ourselves that this is the probability that capital T is less than or equal to little t. Capital T is the random variable. It's kind of an abstract idea, you might say, is what random variables are. They have a technical definition, but I'm not saying what it is. Kind of like an abstract idea, whereas little t represents a true number in the usual sense of the word, a true variable. You do want those numbers to match, those symbols to match as little t's. You want that to be a capital letter there. This formula is always what a cumulative distribution function is, whether the variable is continuous or discrete, like with rolling dice or something. This is the definition of the CDF. For continuous variables, that can be computed as an integral. In general, you want to allow for an integral from -infinity to t, because maybe your PDF is positive for negative values of t. That happens, for example, with normal curves. Of the PDF, little f, I should use a different letter for the variable of integration, like a tau. For our example, we can simplify this. to looking like this. This is since f of t is equal to 0 if t is negative, or maybe I should say f of tau. F of tau is equal to 0 if tau is negative. I can replace the lower limit minus infinity with a 0. And if I also assume tau is, or t is less than 20, or I'll say between 0 and 20, and there I do mean a t for that upper limit instead of the tau, I can replace f of tau with tau over 200. I can use the formula for little f with tau in place of t. When t is between 0 and 20, that's going to mean tau is also between 0 and 20, because tau varies from 0 to t. And in that context, what do I get? Do the integral with respect to tau, get tau squared over 400. Tau goes from 0 to t, giving you t squared over 400 minus 0 squared over 400, which is, of course, 0. So this simplifies to t squared over 400 if t is between 0 and 20. And you didn't need this for finishing the problem. More fully, capital F of t has a piecewise formula. Capital F of t in the long run, if you also consider values of t that are negative and bigger than 20, it's 0 if t is less than 0, t squared over 400 if t is between 0 and 20, and technically it's 1 if t is bigger than 20. And do notice that this quantity, t squared over 400, is 1 when t equals 20. 20 squared is 400. The graph of this is going to be 0 over here, then a quadratic looking about like this, between 0 and 20, and then it equals 1 after you get to 20. That's what the graph of the CDF looks like. CDF is an antiderivative of the PDF. In other words, the derivative of this graph is this graph. The derivative is 0 here and here because the slope is 0. Derivative is positive here and getting larger. It's a concave up graph, reflecting the fact that this graph is increasing in here. Probabilities accumulate faster near 20 because the slope is greater near 20, just like the values of the density are higher near 20. These things are all related to each other. Now, we want to use this for the present value random variable. Z equals 1,000 e to the negative 0.05 times capital T. This is a random variable. Capital Z is a function of capital T. What's going on here? Remind yourself. You've sold a bunch of washing machines. How many we're not saying? Hundreds, thousands, maybe millions. They all have a certain lifetime, capital T. That's random. But random is not completely haphazard. It follows some model. This is our model. Most of them live a fairly long time, but they have a self-destruct at time 20, and they never live to last past 20 years. At a 5% continuous interest rate, 1,000 times this quantity would be the present value of a future $1,000 payment when it dies, like a warranty payment. It's a benefit to the person who bought the washing machine. We're interested in modeling this quantity as a random variable. In other words, we're interested in knowing its PDF and CDF and maybe probabilities related to it and the mean and the median. We could also do the variance and standard deviation, but we're not going that far. We use this CDF method to first figure out its CDF and then differentiate that to find the PDF. Find the capital G first, that's the CDF, then differentiate to find the lowercase g. Let's now figure out the CDF. The CDF, this is the CDF method to figure out the CDF first, and then differentiate to find the PDF. Call it capital G of little z. As with the CDF for capital T, it's a probability of the random variable, in this case labeled with a capital Z, to be less than or equal to the given number little z. That's always what a CDF is. It always represents this probability. Now, T was continuous, and so Z is continuous, and you might say, okay, I guess I have to do an integral to find this. But the answer is no, you don't have to do an integral, because you can relate this to capital F. Because Z is related to capital T. That's why. Just like I showed you last week, replace the Z with what it equals in terms of capital T. Solve the inequality for capital T now. Why? Because that'll relate it to this. That's why. That's our goal. Divide both sides by 1,000 inside the probability symbols. This is all fine to do. Giving you, as the example last week, Z over 1,000. In fact, this is just like the example from last week, except for the fact that the PDF and CDF of capital T are different. The little f and capital F are the things that are different now. But everything else is pretty much the same. Isolate capital T, isolate capital T. I guess I need to get rid of the E. Take the log of both sides in the inequality. That is okay to do. And keep the inequality in the same direction, because the logarithm is an increasing function, is the technical reason why this is okay. Now we're almost solved for capital T. Divide both sides by negative 0.5. Which is equivalent to multiplying both sides by negative 20. 1 over 0.05 is 20. But the inequality does change direction when you do that, because I'm dividing or multiplying both sides by a negative number. But that's okay. This is the probability of something happening. It's going to equal 1 minus the probability of it, the opposite thing happening. Change the less than or equal to a, or the greater than or equal to a less than. That's the opposite event. It's like saying, this is the event that it's going to rain, and that's the event that it won't rain tomorrow. A more abstract version of that kind of idea. But then you might object and say, hey, I've got a less than there. I really want a less than or equal to, because after all, I've got a less than or equal to here. But the variable is continuous, so you can replace less thans with less than or equal to. That's only because the variable, capital T, is a continuous variable. It takes on all values conceivably along a continuum, in this case between 0 and 20, for a lifetime of the washing machine. T is continuous. Sounds a little strange to say that, because it's like, well, where's the function? Is it a continuous function? Is that what I'm talking about? Yes, but not. I'm not trying not to get into details. Intuitively, it takes on all values along some interval in the number line, conceivably, with positive probability. This is now probability of capital T being less than or equal to something. Just like this is the probability of capital T being less than or equal to something. The something here is just a plain old little t. The something down there is that crazy thing. But it's still the same principle. This is capital F of negative 20 ln of Z over 1,000. I need to also subtract that from 1. What happens when I do so? Let's assume we're in the case that we're most interested in, where the input is between 0 and 20. Assume the input, negative 20 ln of Z over 1,000, is between 0 and 20. Wait a minute, does that make sense? Shouldn't this quantity there that I'm pointing at be negative? Not for this example, it's not. Z is the present value of a future $1,000 payment. It's going to be less than $1,000. So Z over 1,000 will be less than 1. ln of a number less than 1 is negative. Graph the ln is negative over here. Negative times negative is positive. This is a positive quantity, or at least a non-negative quantity. I want to now use the formula in that case, t squared over 400. Replace t with the crazy thing. T squared, negative 20 ln of z over 1,000 squared over 400. Negative 20 squared is positive 400. Positive 400 divided by 400 is 1. The 400s cancel. And you're left with 1 minus ln of z over 1,000 quantity squared. There's capital G. If we assume negative 20 ln of z over 1,000 is between 0 and 20, what does that mean about z itself? I'll let you check this. It turns out to mean that z itself is between 1,000 over e and 1,000. I mean, think about it a little bit. If this quantity equals 0, that means the ln is the thing that's 0, which means its input is 1, which means z is 1,000. On the other hand, if this thing equals 20, and you solve for z, you'd have to divide both sides by negative 20 and get a negative 1 over here, and then exponentiate. Get an e to the negative 1. And you'd also have to multiply both sides by 1,000. What is 1,000 over e? Approximately, it's 300 something. 1,000 over e. It's about 367.88 as an approximation. They have the drop dead data 20 years. That's where they have the self-destruct. The present value is not going to be smaller than that. You're going to make the payment before 20 years. So that's the CDF. What's the PDF? You don't have to do anything other than just differentiate the CDF. That's all you have to do. Little g is the derivative of capital G by definition of what these things are. Or you could argue by the fundamental theorem of calculus. For example, here, when you differentiate this capital F, notice the variables in the upper limit of the integral. FTC part 2 in chapter 6 would say the derivative of capital F is little f. Similarly, the derivative of capital G is little g. So differentiate this. Derivative of 1 is 0. Derivative of this thing, I need to use the chain rule, in fact, a couple of times. Like this. That's little g unsimplified. The thousands cancel. Simplifies to negative 2 ln of z over 1,000 divided by z. Still z is between 1,000 over e and 1,000. There's the PDF. What does the graph of this PDF look like? I think it looks something like this. It's actually a decreasing function. I think it looks something like that. Between 1,000 over e and 1,000. It's higher at lower values than at higher values. Does that make intuitive sense? Just think about these kinds of things. It's saying for most of the washing machines, based on when they fail, the present value is smaller, where the density is higher. That's analogous to the fact that for the actual lifetimes, most of them lasted a long time. When they die further in the future, that corresponds to a smaller present value. You don't need to save as much right now to make that future payment of $1,000 when they break. Yes, this does make sense intuitively. There's what little g looks like. You didn't have to graph that, but I did. It is right skewed. You got a long right tail here where the values sort of stretch out toward high values. Those are the outliers, so to speak. Most of them are down here. The outliers affect the mean more than the median, though. The mean should be bigger than the median. The mean is going to be further to the right than the median is. But now, how about finding probabilities, the mean and the median? How about finding those things? For the probability that we were after, that Z was between 600 and 800, by definition, that's the integral of the PDF from 600 to 800. Right? That's the purpose of PDFs. Part of the purpose is to find probabilities like this by integration. Which means, I guess we'd have to integrate this thing, which doesn't look like it's so easy. Can be done with substitution, but you don't have to, because we already have an antiderivative right there. Use the CDF. This is capital G of 800 minus capital G of 600. Because capital G is an antiderivative. Use the formula for capital G. Again, it's this thing, 1 minus ln of Z over 1,000 quantity squared. 800 over 1,000 is 0.8. When I plug in 600, I get ln of 0.6. The ones cancel. If you distribute the minus sign through and rearrange, you get ln of 0.6 squared minus ln of 0.8 squared. By the way, you can use another antiderivative, like maybe just this without the 1 in front, to save a tiny bit of time, a tiny bit of work. But this is fine. ln of 0.6 squared minus ln of 0.8 squared. There we have the 0.21115. Just like I said the answer was. For the mean, mu. Mu kind of looks like an M, kind of looks like a U. Mu is the mean. If you got a mean of data, you call it X bar. If you got a mean of a distribution, you call it mu. You find it by integrating the variable times the PDF. In general, from minus infinity to infinity, but for our example, that simplifies to 100 or 1,000 over e to 1,000, because that's the domain of G, where little g is negative 2 ln of Z over 1,000 divided by Z. Looks pretty complicated, though it does simplify a bit. The Z's cancel. You can bring the negative 2 out in front. Negative 2 times the integral from 1,000 over e to 1,000 of ln of Z over 1,000. This is a positive quantity in spite of the negative sign right there, because when Z is between 1,000 over e and 1,000, it's less than 1,000. Z over 1,000 is less than 1, and so ln of that is negative. You're integrating a negative quantity here to get a negative integral, times a negative number there will be a positive number in the end. This integral can be done by hand. You can use parts. Let u equal Z over 1,000. Find u prime. V prime is 1. V would be Z. And then use integration by parts to do that. It's doable. For sake of time, let's just use Mathematica here. Negative 2 times the integral from 0 to 1,000, or 1,000 over e. Type it in as a capital E, to 1,000. ln is log in Mathematica. Should be a positive number. There it is. What should it be approximately? It should be closer to 1,000 over e than it is to 1,000. Should be closer to 368 than 1,000. Halfway between 368 and 1,000 is somewhere around, 600 something. This should be less than 600 something, hopefully. Yes, it's 528. That was the answer I gave you. This is about 528. That represents a dollar amount. So if you've got millions of customers, here's the practical implication. If you've got thousands or millions of customers, a lot of customers buying your washing machine, and you're offering this $1,000 warranty payment whenever the washing machine dies, if you have available to you a 5% continuous interest rate to invest money right now, you should invest at least this much per washing machine right now to be able to make those payments in the future. Now, of course, you'd want to give yourself some cushion. You probably want to invest more, look for a better interest rate, but that's the basic idea. That's the application. Being a right-skewed distribution, however, the median is a better measure of a typical payment, you could say. What's the median? Median, I'll call it, how about Z sub med? This has nothing to do with medicine, seemingly, but med means median here. We need to solve for when the value of the CDF equals 1/2. What is the CDF here when Z-med is between 368 and 1,000? It's 1 minus ln of Z-med over 1,000 squared. This means the ln of Z-med over 1,000 squared is equal to 1/2. Take the square root of both sides. And you actually want to take the negative square root, not the positive square root, because Z-med's less than 1,000. So ln, you're going to get ln of something less than 1, which is negative. So you need that negative square root because Z-med over 1,000 is less than 1. Then get rid of the logarithm by exponentiation, multiply by 1,000. In the end, Z-med looks like it's 1,000 e to the negative 1 over root 2. 1,000 times e to the negative 1 over root 2, about 493. About half the present values of these future payments are less than 493 and about half are bigger. Let's confirm this with simulation. I'm about to show you something really cool in Mathematica, I think. It's a way to define your own PDF, define your own distribution, and use RandomVariate still to do simulations. So I can type in the original PDF for capital T over 200, and use probability distribution, a built-in command with that capital F of T in here for T between 0 and 20. These are the lifetimes. I'm going to give this thing a name. Mathematica tends to, the help menu tends to call it script D. I made that cursive looking D by doing escape SC escape. Oh, no, escape SC capital D escape. Not that you have to do that. Enter that. Seemingly nothing happened, but now I can get some data values for lifetimes by doing RandomVariate. Script D, say 100 data values. There we have it. These are 100 simulated lifetimes. Notice they're more typically close to 20 than they are to 0 for this triangular distribution. I could also define a function, I'll call it h of z, that is the present value. 1,000 times e to the negative 0.05. Actually, probably should call it t here. Negative 0.05 t. That's the function z equals 1,000 e to the negative 0.05 times t, using ordinary variables. I believe if I apply this function to data, t, I'll get a corresponding simulated present value data set. Yep, a bunch of numbers, all bigger than 368 and all less than 1,000. And yeah, more low numbers than high numbers. And let's confirm that the mean and median seem about right, but I'm going to do more data points, but I'll suppress the output with a semicolon. What's the mean of my data set? For Z, hopefully it's close to 528, the theoretical mean. Yeah, pretty good. What's the median? Hopefully it's close to 493. Yes, not too far away. You want to play it extra safe, try 10,000 simulated data points. Again, the semicolon just suppresses the output. Mean is close to 528 still, median is close to 493. Just like we got with the theory. Confirming the theory seems right. Two purposes of simulation. One purpose is to confirm theory. One is to do simulations when the theory is just way too hard.